Let's find a formula for the potential of a line of charge. We start by drawing a picture. Our line will be on the x-axis. The point P where we want to calculate the potential will be on the y-axis at a distance z from the line. Let's consider an infinitesimal element, dx, of the line. Alone it behaves pretty much like a charged particle. The distance dx is from point P varies with x. The line has a linear density lambda. So an element of charge is lambda times an element of the line. For a single charged particle we have this formula, which I'm not showing how to derive here. I assume you know it. That formula gives the potential for a given charge, q, so an infinitesimal part of the potential is related to an infinitesimal part of charge. The distance p is from dx is just the hypotenuse of the right triangle we see in the picture. Let's set up the expression for an infinitesimal potential now. We substitute dq for lambda times dx and r by the value of the distance between p and dx. All we have to do now is to integrate this expression with respect to dx, x vary from 0 to L. Here we set up the integral. It is not so easy as it looks. Constant terms come out of the integral. This little monster requires trigonometric substitution. Let x be equal to z times the tangent of theta. So, dx is going to be z times the secant of theta squared. Just trust me this time, I'm not showing how to do this derivative. Now we substitute x in the denominator by z times the tangent of theta. Remember trigonometric identities? The expression in parentheses turns out to be just the secant of theta squared. To see why, use the identity, sine squared theta plus cosine squared theta equals 1. Then divide by cosine squared theta on both sides. Now we substitute these values in our integral, that is, dx on the top. The exponents in the denominator cancel out beautifully. Even more terms cancel out now. What is left is the integral of the secant of theta. So we use trigonometric substitution to get to a trigonometric integral. But this one is easier. It is stuff from Calculus 1. This is one of the trickiest things I ever saw in mathematics. Multiply the secant of theta by the correct 1. Whoever came up with this idea first was an actual genius. Just multiply now. Now we use a simple u substitution for the denominator. And then we have to find out what du is. We rewrite these identities to understand what is happening. Now we differentiate them by using the quotient rule. Here we just rewrite everything. Let's factor out a cosine theta from the denominator of the first term. For the second term, notice that we can use the same trigonometric identity as before, so its numerator becomes 1. So now we have the value of du. We substitute everything into the integral now. And we can cancel out this horrifying thing. So the integral is just the natural logarithm of the absolute value of u. Again, just trust me. I'm not showing how to get to this one either. We need to change our variables back to x and z. Let's draw a right triangle. Remember this substitution we did earlier, let's use it to go back. Now it is easy to see what the secant of theta is. Let's go back from u to secant of theta plus tangent of theta. And finally we substitute these trigonometric expressions by their value in terms of x and z. Common denominator, so we can simplify. And here we apply a logarithm property. The log of a quotient equals the log of the numerator minus the log of the denominator. Notice that we are dealing with an indefinite integral, so guess who is this constant term on the right? Yes, it is our constant c. And here is the indefinite integral of the secant of theta in its full glory. Wait, what was I doing exactly? I'm pretty sure it was important. Of course. We were trying to find the potential at a point P due to a charged line. Let's just use the integral we found. We can use the logarithm property once more to simplify this expression. And this is it. The formula for the potential of a line of charge at the point P, which is at a distance z from it.